Now I would like to say a little bit about polynomial approximations. So let's remember a little bit about how polynomials work. So let's write down our notation. So a polynomial of degree at most n is a function that looks like this. P of x, polynomials, you're allowed to have constants. You're allowed to have linear terms, so that's x. You're allowed to have quadratics, x squareds, multiplied by a constant. And then being of degree at most n means you stop at x to the n. And I'm going to write that with a sigma. Sum from k equals 0 to n, ak x to the k. And now we assume you're all familiar with polynomials. So if c is a real number, you can write polynomials not as powers of x, but as powers of x minus c. And one technicality I want to point out is that you want to be able to evaluate polynomials at 0, but if we just plug 0 into one of these sums, or if we plug c into this second sum, we get 0 to the 0 showing up. And we don't want that, so we take 0 to the 0 equals 1 in this particular indefinite form. That will be your a naught is a naught times x to the 0, even if x is 0. And we love polynomials. Polynomials are our favorite function. They're easy to evaluate. All you have to do is add things and multiply things. You can program a calculator to evaluate polynomials really easily. You can do them by hand with only moderate amounts of pain. Finding something like a logarithm or a cube root or a sine by hand, conversely, that's a huge pain. So we like polynomials, and we'd like to be able to approximate other functions with polynomials. So let's talk about how we do that. So let's let f be a function whose domain is, let's say it's an open interval. And let's suppose that f is particularly nice or well-behaved at a certain point, C in its domain. So what do I mean by nice? Let me give you a couple of examples. So for example, if we let f of x be the square root of x, then the square root of x is particularly nice at the point 1, 4, and 9. I can tell you what f of 1 is. It's 1. F of 4 is 2. F of 9 is 3. I can't tell you off the top of my head what f of 5 is. It's some extremely nasty decimal. It's not a nice round number. Other examples would be something like f of x is the logarithm of x, which is particularly nice at 1. I know what the logarithm of 1 is or something like f of x equals e to the x. I know what e to the 0 is. If you ask me to tell you what e to the 1 is, it'd be some horrible old decimal. So lots of functions that we care about deeply. They're very well behaved at one value. Often it's 0, but sometimes it's 1 or 4 or something. And they're not very well behaved anywhere else. They're hard to deal with. You get these horrible decimals, so we'd like to come up with a polynomial based just on the behavior of f of x at the point C. Yeah. So let's let P be the polynomial, or a polynomial of degree at most n, and then we want P of C. So we said f was well behaved at C, so let's let P of C be equal to f of C. And we'd also like to say a little bit more about this polynomial, so let's suppose that they've got the same derivatives at this point. And you may recall that say the derivative of e to the x is e to the x, so all the derivatives of our f of x in this example, they're also going to be easy to compute at c equals 0. Derivative of L log x, at least if it's a natural number, ln x, then your derivative is 1 over x. So those things are easy to deal with at c. And then derivative of square root of x, you can use our inverse function theorem. We've got 1 over 2 times the square root of x. You get square roots of x showing up in the denominator of the derivatives. So that's going to have the same good points as the actual polynomial, as the original function. And let's say we want all the other derivatives to match up. And our notation is the kth derivative is p to the power of k in parentheses. Let's say, and let's see how many derivatives we can get and what we can say about our polynomial p. Well, let's remind ourselves what the derivative of a polynomial looks like. So p of x, that's the sum from k equals 0 to n, bk, then x minus c to the k. And then if we differentiate that, we just get the bk's and then a k and an x minus c to the k minus 1. And we're going to start this at 1 because if k equals 0, then we've just got our constant term b naught. And when we differentiate that, it goes away. Second derivative. Similarly, we can start at 2. And I forgot a k minus 1 here. And then it's a pretty straightforward induction argument to show that if j is less than or equal to n, then the jth derivative, that's the sum from k equals j up to n, bk, and then we've got k factorial over j factorial. That's k times k minus 1 times k minus 2, and then we stop at 1 more than k minus j. That's why we're dividing by j factorial. then x minus c to the k minus j. And then, so if we plug in a c, the jth derivative of p at c, then we get c minus c to the k minus j. And then that term, this is 0 unless it's 0 to the 0, because we're taking 0 to the 0 is 1. So the only term that survives is the term where k equals j. So we get a bj and then a j factorial. And of course, this is the derivative if j is between 0 and n, and then the jth derivative, any higher derivative is 0 if j is strictly greater than n. So the first derivative of a constant is 0, the second derivative of a linear function is 0, the third derivative as a quadratic is 0, and there's nothing you can do about that. So let's put it all together. The polynomial p of x, sometimes we write pn of x. This is the sum from k equals 0 to n because it's a polynomial degree n. And then our bk times k factorial is the derivative. So we write down what we want the derivative to be. That's the kth derivative of f at the point of c. We divide by k factorial, takes x minus c to the k. That is this is the only polynomial of degree at most n such that the kth derivative of our polynomial matches up with the kth derivative of f at our point c. And this is for all k between 0 and n. So there's one and only polynomial that has this nice property. So this polynomial, it's exactly equal to f at this point c, and all the derivatives are nice. And then the point of Taylor's theorem is to say, okay, this polynomial is supposed to be an approximation to f. How good of an approximation is it at points other than our special point c? And to answer that, here is Taylor's theorem. Here is theorem 2.5.6 in your book. So let's let c be a real number in the interval from a to b. Let's let n be a natural number. Let's say it's at least 1. F is a function from this interval to the real numbers. And we're going to require that the kth derivative of f exists and is continuous everywhere in this interval from a to b. And we're going to require that the top derivative, the nth derivative, has to exist at least at our point, at our special point c. And let's let p of x be the polynomial approximation that we spent so much time talking about above. And then here are the following two things are true. The first thing is that f of x is equal to p of x plus h of x times x minus c to the n. Okay, so that's not too hard. You just let h of x be f of x minus p of x over x minus c to the n. And for some function, h that is continuous, on this interval. Particular, it's continuous at c. And not only is it continuous, it's 0 at c. And even better, if I've got one more derivative, then I can actually give you a formula for h of x. So if the n plus first derivative, if this exists, for all x in AB, and you could even just have it exist for all x except your special point, if that happens to be convenient, then let's write this as for every z in this interval, there is a y that's between z and c, such that our f of x is p of x plus, and then you've got x minus c to the n plus 1, and then you can write n plus 1 derivative of f at y over n plus 1 factorial. And let's go ahead and prove Taylor's theorem. So here's part A. So first off, let's define h of x. It's exactly the function you think it's got to be. It's going to be f of x minus p of x over x minus c to the n if x is in the domain of f and is not the point that would make us divide by 0, and it's 0 at our point in c. And then f and p and x minus c to the n are continuous. On AB. So h is continuous except at c. So all we need to prove is that h is continuous at 0, and by corollary 2.1.3, all we need to prove is that the limit of h of x as x goes to c is equal to 0. And then, so how do we prove this? We use L'Hopital. Now notice that f is different, that f is continuous except at C is continuous at C, p is continuous at C, and they have the same value at C, so the limit of the top as x goes to C is 0. And the limit of the bottom as x goes to C is 0, so we're allowed to use L'Hopital's rule. Recall we've assumed that all the derivatives of order up to k minus 1 exist. I suppose I forgot to say that up here, so let me write that in. Now we keep going. We're going to keep applying L'Hopital's rule up until we get to the n-1 derivative. Now we could apply L'Hopital's rule one more time, but I didn't want to assume that the nth derivative of f was continuous. I suppose I could have made that assumption, but I didn't want to. So let's see what we've got here. We've got our 1 over n factorial, and then we've got fn minus 1 of x. We've got an x minus c in the denominator. And then what is the pn minus 1th derivative of x? Well, this is a p is a polynomial of degree n. And so if you take n derivatives, you get a constant. So if you take n minus 1 derivatives, you get a linear function. And the linear function you get is pn minus 1 of c plus x minus c pn of c. So we know it's a linear function because you take one more derivative and you get a constant, and that linear function has the right value at c and the right derivative at c, so we can write it like this. Limit as x goes to c, 1 over n factorial. Then we write f n minus 1 of x minus, and then remember how we define our polynomial. It's supposed to have the same derivatives as f everywhere, so we can write and then we've got the other bit, the nth derivative of p, which is the same as the nth derivative of x at the point c. And then we've got an x over c and an x over c that cancel out, and I'm not going to write them down. And notice that the first part, this part approaches f prime of c as x goes to c, and then this part is the derivative of that is the derivative of fn minus 1. So this limit is indeed just 0. So h is continuous at c by corollary 2.1.3. All right, now let's prove part B. So let's pick an x in this interval in the domain of our function f that's not our target point C. That's not our good point where we know our polynomial approximation matches our function perfectly, and we will consider just for the sake of variety, the case where x is less than c. So x is between a and c. And you'll have a homework problem that's similar to Taylor's theorem, where I think I'll let you consider the case where x is bigger than c. So let's let m be this quantity, f of x minus our polynomial p of x, and then you divide it by x minus c to the n plus 1. So m depends on x and c. And now let's let g of y be this function. It's f of y minus p of y, and then we subtract off m times y minus c to the n plus 1. Now, I want to emphasize we're thinking of x and c and f and n. We're thinking of all of those as constants. We're picking an x and a c and an f and an n, and we're fixing them for the rest of this proof. And then g of y, as far as this function g is concerned, y is the only variable in the world. So we're going to be finding the y that is this y up here in the statement of the problem. That's what we're thinking of as our variable. So m, I gave you a complicated expression for m with x's and c's and n's in it, but for now we're going to think of m as being a constant. Then here's some things to notice. First of all, your polynomial and your y minus c to the power of n plus 1, those are smooth. Those have as many derivatives as you want. And m, as I've just said, is a constant. Our function f, we're assuming, has n plus 1 continuous derivatives. So we're going to notice that the n plus 1 derivative of g that exists for all y between a and c. Particular g prime, g double prime up to n plus 1 derivatives exist at the point x in particular, but more generally it exists for all y in that little interval. Remember that differentiable implies continuous. So if you're a differentiable function, you must be continuous. So that means the nth derivative of g is continuous on the interval from a to b. And so the n minus 1th derivative, since the nth derivative is continuous, it exists. So the nth minus 1 derivative exists. And all the way down to g prime and g they are all continuous on this interval from a to c. All right. Next thing I want to bring to your attention, what is g of x? G of x is f of x minus p of x, and then we subtract from that our constant m, which was f of x minus p of x over x minus c to the n plus 1. and then we plug in x for y, we get an x minus c to the n plus 1. An awful lot of cancellation is going to happen, and we get g of x equals 0. Now let's think about what is g of c? G of c is f of c minus p of c minus, I don't care what m is at this point because I'm multiplying it by c, minus c to the n plus 1. So g of c is also 0. Finally, let's differentiate g. The kth derivative of g, derivative with respect to y, is still treating m as a constant. That's the kth derivative of f minus the kth derivative of our polynomial. And then when you differentiate a y minus c, we're going to get n plus 1 factorial and n plus 1 minus k factorial y minus c to the n plus 1 minus k. Every time you take a derivative, you lose a power of y minus c, and you lose a number, n plus 1, n minus 1, n minus 2, and if you check carefully, you'll see that we've got the right denominator written here. So in particular, if k is less than n or equal to n, then gk of c is indeed equal to 0. Now, we did part A with repeated applications of L'Hopital's rule. We're going to do part B by repeated applications of the mean value theorem. So, by the mean value theorem, there is a y1 with, this isn't the y we're finding, this is another y with y1 between x and c, and g prime of y1, that's g with one derivative of y1, that's g of c minus g of x over c minus x, but notice both of those things are 0. All right, so then we apply the mean value theorem again. And we're applying the mean value theorem to g prime. So g with two derivatives of y2, that's g double prime of y2. That's g prime of y1 minus g prime of c over y1 minus c. I suppose I've got them in the other order. The denominator is negative, but that doesn't matter because the numerator is positive. All right, so we're going to keep doing this. So let's suppose that yk is between x and c, and k derivatives at yk equals 0. And let's say k is less than or equal to n. Why do I want it less than or equal to n? Because of this condition up here, that if k is less than or equal to n, then I can take k derivatives at c and get 0, and notice that that is important. Then by the mean value theorem, there is a yk plus 1 with between yk and c, which means it's between x and c, and such that if I take k plus 1 derivatives evaluated at yk plus 1, that's the same as taking k derivatives and then taking one more derivative. Then because gk of c is 0, because k is less than or equal to n, we get 0. So, cool. So now what are we going to do? Now we are going to let y be our y n plus 1. Now, because n is less than or equal to n, we can generate a yn plus 1. Because g has n plus 1 continuous derivatives. We can't generate an n plus 2. We didn't assume we had that many continuous derivatives. So we didn't assume we had that many derivatives, but we do have n plus 1 derivatives. So that's what our y is. Then we've got that 0 is the same thing as g with n plus 1 derivatives at our point y. But then g with n plus 1 derivatives, that's f with n plus 1 derivatives, minus p with n plus 1 derivatives. And then we subtract m times n plus 1 factorial. And so that's true. But remember, p is a polynomial of degree at most n. So we only go up to y to the n. So that term is, so if we take n plus 1 derivatives, it's like taking a derivative of a constant or two derivatives of a linear function, we get 0. So we can write this out without the p. So then rearranging things, the n plus 1th derivative of f evaluated at y is m times n plus 1 factorial. And remember what m was f of x minus f of c over x minus c to the n plus 1. Sorry, f of x minus p of x. And then rewriting a little bit, f of x is just p of x, and then fn plus 1y over n plus 1 factorial, and then last off we've got x minus c to the n plus 1. And that completes the proof of Taylor's theorem. 2 comments. The first is that if you look in the book, this is not quite what you see, and that is because there are typos in the book. So as an exercise, what is wrong with the theorem in the book? What goes wrong with this theorem statement, and what goes wrong with the proof? And here is a fact. Another fact is that there are other forms of the remainder. So, for example, it turns out that f of x is equal to our polynomial, and then there is always a y, and then instead of having an x minus c to the n plus 1, we've got an x minus y and an x minus c showing up. This is called the Cauchy form of the remainder, the one, and we know and love from Taylor's theorem is called the one we proved above is the Lagrange form. And you will prove the Cauchy form, maybe not with quite as good a constant, but that's okay, on the homework. And you'll also see a way to generate lots of different forms of the remainder. So if you wanted a x minus y squared and x minus c to the n minus 1, you'll see on the homework how to do that.